Hello. In this group of lessons in this unit, we move on from the beginning look of statistics and look at some properties within probability, and the two are definitely interconnected, but they have their differences as well. So just to begin, if you're following along the note packet, this isn't in there. This is just a little lead-in background information for you. So probability is distinguished from statistics in that while statistics looks at data and the conclusions and inferences that you can draw from it, probability kind of deals with what's going on in the background under the hood. What are those random processes that are playing out, and why are the data kind of doing what they are doing? So by its definition, probability is the measure of the likelihood that an event will occur. Just some etymology for you. The word probability comes to us from the Latin word probabilitas, which is a measure of the authority of a witness in a legal case in Europe. So it was used to measure how honest and upright the person was in terms of being able to give their case. So that's some background information in regard to probability. Where did probability get its start? So probability's been around for thousands of years in the terms of the fact that many cultures played games, and then into the 15th century in that area, maritime companies used to give out insurance plans. If you're going to go out to sea and you had a large cargo load, you would want to insure that. So they gave out insurance plans, and they gave them out at certain odds. You pay this much, we'll pay back this much if you happen to get into an accident. So, but those calculations were based entirely on intuition. There was no mathematical calculations going on. The actual formal study of probability began with gambling inquiries and with two mathematicians known as Fermat and Pascal, and a famous question known as the problem of points or division of stakes. There's also another item that they were considering, another gambling question. And it's because cards and dice are inherently probabilistic. So here's the situation that we can relate to that they were considering. So let's say two players are gambling. Each game is worth $1. So to gamble, each player puts in $50, and the winner is going to take home all $100. Assuming each player is equally likely to win each game, how should the money be split if the score is 9-7 when the game needs to be ended? So the story goes that the game needed to be ended. It was going late into the morning. Each game took an hour or so, and they didn't want to be continuing on into the next day. And so they wanted to end the game, and the question was, how do you divide up the money? So what ideas do you have? You can maybe pause the video, think through some for yourself before we get to it here in a couple slides. So to start, though, we're going to define some terms that we're going to need going forward. Anything underlined in red is where there would be a space in your note packet to fill those in. A probability experiment is an action or trial through which specific results, counts, measurements, or responses are obtained. So it's any action where we're going to be recording some results. And the outcome is the result of a single trial in a probability experiment. It's what happened. The sample space is the collection, the set of all possible outcomes that could have occurred from a probability experiment. An event consists of one or more outcomes and is a subset of the sample space. It's denoted with an uppercase letter. A simple event is when an event consists of a single outcome. Such example would be like tossing a heads or rolling a 3 or maybe drawing a heart or something like that. So an example would be the event tossing a heads and rolling an odd is not simple. The reason why is because there are multiple items that are combining together, multiple outcomes that are combining together to make a single event. So those are the definitions that we need. We're going to start by making what are known as a tree diagram. So here's the situation. A family is told they're going to have twins, state the number of outcomes, and identify the sample space using a tree diagram. In probability, we need to know all of the possible outcomes so we can see the portion of the entire set of outcomes, which we call the sample space, that verify our original condition. So if we're going to have two kids, because they're going to be twins, this is the first child. The first child could either be a boy or a girl. And then the second child could also be a boy or a girl. So even if the first one's a boy, the second child could be a boy or a girl. And even if the first child's a girl, the second child could be a boy or a girl. And then we just list out all the possibilities. So I could have boy and then boy. So we'd say boy, boy. I could have a boy and then a girl. So we'd say boy, girl. We could have a girl and then a boy. So we'd say girl, boy. And then we could have a girl and then a girl. We'd say girl, girl. So the number of outcomes, we can see there are 4 outcomes. The sample space, and because it's a set, we use curly brackets to denote it. We could have had, like I said, let's use red. boy, boy. We could have had boy, girl. Could have had girl, boy. And we could have had girl, girl. And that is how you list the sample space. Now we have a little bit of enough background information to kind of go back to look at the situation that Fermat and Pascal were looking at. So returning to the situation with the division of winnings in a game to 10, how should the winnings, the $100, be divided for a game where Pascal is currently ahead 9-7 against Fermat? So note, there are two schools of thought. Let's see which one you agree with. So the first school of thought, option one, is this. Let's just list out the 4 ways the game could end. Since Pascal is already ahead 9-7, once Pascal, wins, that would be done once he gets to 10. So the first option would be Pascal wins the first game. That would be over. Maybe Fermat wins, then Pascal wins. Maybe Fermat, and then Pascal. And the only real way for Fermat to win is he has to win 3 in a row. So since there are 4 ways the game could end and Pascal wins 3 of them, one school of thought is Pascal should be paid 3/4, because there's a 75% likelihood that he'll win, and 75% of $100 is $75. So he should receive $75. The second school of thought is this. Since at most 3 games can be played, let's list all of the ways that 3 games could occur. And in order to do that, I can use a tree diagram. For any game, I could have Pascal or Fermat winning. This would be similar if I asked you to make a tree diagram for a family that had 3 kids. You would just replace the P's and the F's with boys and girls. So the first game could be Pascal, then Fermat, and then the second game again, Pascal and then Fermat, and then Pascal and Fermat. So you list out all the possibilities. You could have Pascal, 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 Fermat, listing all the way down to the last case where you'd have Fermat, Fermat, Fermat. Well, there are 8 different ways that the 3 games could be played out, and in those 8 games, Pascal wins 1 of them, and that's all he needs in order to win get to 10. So since he wins 7 of the 8 possible games, he should be paid 87.5%, which would be $87.50. So these are the 2 schools of thought. And we need to decide because there are different payouts depending on the schools of thought. So you can pause the video now and maybe think about which one you think is the most fair before I share with you what has been accepted as the most fair and why we logically accept that. So we choose option number 2. And the reason is this. The second is the most fair because if you're going to allow Fermat the benefit of playing out 3 games and having the result count, the same must also be for Fermat, this should be for Pascal. The same must be true for Pascal. The downside of this option right here is if I just list Pascal winning the first game, that is not all of the ways that he could have won with a P starting off. If I look right here, there's actually 4 different ways in which those 3 games could have played out with P starting off. And so I'm kind of shortchanging him by doing that. So if I'm going to give Fermat the benefit of playing out 3 games, I need to do it for Pascal as well and count all of the different ways in those 3 games he could have won by getting at least one of the wins as separate identities, separate events, outcomes. Otherwise, I'm going to shortchange him. So we would give Fermat $87.50, and that is the beginning of probability by making tree diagrams. But you'll notice tree diagrams, they can be kind of cumbersome. They take a while to make, and there's some actual easier patterns going on. So for example, this isn't in the notes, but you can just follow along, and we're going to develop a new principle in order to simplify the process. Consider the following situation. Each turn in a board game consists of tossing a coin and then rolling a die. Determine the number of outcomes for each turn. Well, at first, we could do what we did before. We'd make a tree diagram. The first part of the tree diagram would be heads and tails, and then if it was heads, you'd roll the dice, and you could get 1 through 6. So you could get a heads and then a 1, a heads and then a 2, ... heads and then a 6. You could have flipped the coin and got a tails. It'd be tails and then a 1, tails and then a 2, ... tails and then a 6. And if you look, there's 1, 2, 3, 4, 5, 6, and then another 6 over here. There are 12 different outcomes. The sample space would look like the following: H1, H2, all the way down to tails 6. However, this isn't really necessary if I'm just considering the number of possible outcomes. What I can do instead is look and say, oh, there were 2 branches to start off with it, and each of those branches had 6 more, and hey, 2 times 6 is going to leave me with a 12, and we call that the fundamental counting principle. So the fundamental counting principle can be used if one event can occur in m ways, a second event can occur in n ways, then the number of ways in which the 2 events can occur back to back would be m times n. You could extend this for any number of events, so it doesn't have to be 2. You could do this for 3 or 4. You just keep multiplying down the line. So in our example, in each turn in a board game consists of tossing a coin, then rolling a die. How many possible outcomes are there? Well, there's 2 outcomes for the coin times 6 outcomes for the die, which leaves me with 12 possible outcomes. We call that the fundamental counting principle. This fundamental counting principle is useful in a variety of different situations. It can be used in counting number of passcodes, like in this personal identification number. It can be used in determining the number of license plates that could be valid in a state. Tons of different applications. So we'll consider the following: the PIN. If you've ever used a debit card, you're familiar with a PIN. The PIN is the personal identification number for a debit card, and let's say it consists of a 4-digit code. How many codes are possible if no digit can be repeated? So that means for the first place, there are 10 numbers possible. For the second number now, there are only 9 options possible because no digit can repeat. So if the first number was a 3, I can't choose 3, so there's only 9 numbers possible. Then in the third one, there'd be only 8 because I've already used 2, and then the last one, there'd be 7. So 10 times 9 times 8 times 7. If I multiply those out, I'm going to get 5040. So 5,040 different ways to make a PIN if no digit can repeat, if all of the digits have to be unique. If each digit can repeat, that means there are 10 options for the first one, and then 10 options for the second, and 10 options for the third, and then 10 options for the fourth, which is 10 to the fourth, or 10,000. So you see, just by restricting the fact that no digit could repeat in situation A, I've pretty much cut my possibilities down to half. Last case, let's say repetition is allowed, but your PIN cannot begin or end with a 0. So the first number in my PIN, there are only 9 options because I can't begin with a 0. Then I could have 10 for the second times 10 for the third. And again, the last one, again, only 9 options because it can't begin or end with a 0. So 9 times 9 is 81. And then 10 times 10 is 100, so I get 8100. There are 8100 different ways in order to make that PIN. So you can see how the counting principle is very helpful to keep track of the number of different possibilities. Going to give you a chance to try. So here's this situation. Realtors use lock boxes to store keys on houses that are for sale so they can come up and type in the code and then obtain the key. The access code consists of 4 digits. The first digit cannot be a 0, and the last digit must be odd. How many codes are available? And going forward, unless noted, we will say repetition is allowed. So pause the video now, give yourself a chance to try. This is how you should have thought about it. First digit can't be a 0, so there's only 9 options for the first number. The second and third can be anything, so 10 options and 10 options. And then the last one can be anything, except it says it needs to be odd. So the odd numbers 1, 3, 5, 7, 9. There are 5. So 9 times 10 times 10 times 5. There are 4,500 different possibilities. That kind of ends the first beginning ways of counting. I can make tree diagrams. I can use the counting principle. We're going to move on now to kind of talking about where probability gets used, and that's in terms of calculating percentages or portions of the total outcomes. So there are 3 different types of probability. The first is classical or theoretical probability, and that's when each outcome in a sample space is equally likely. We take the number of outcomes in the event and divide by the number of outcomes in the sample space. It's essentially successes divided by the total number that were possible. The second is empirical or statistical probability, and that's basing observations in order to determine probability. So you run an experiment and you use data to determine the probability, so relative frequency of an event. So the difference between classical and empirical would be something like, flipping a coin is a good example. Classical, we would say there's a 50% likelihood that I could get a heads or tails. So if I flip a coin 100 times, classically I would expect 50 heads and 50 tails. Empirical would be, maybe I don't know that off the bat. Maybe I want to know what's the likelihood of attaining heads or tails, so I flip a coin 100 times and I get heads 53 times. Empirically, then I would say the probability of getting heads would be 53% because I'm basing it on my actual data. And so that's the difference between basing probability on data and basing probability on theory. The last one and the least used is kind of where probability got its start, and that's subjective probability. Intuition, that was that maritime example when companies would give out insurance plans based on just kind of thought. So intuition, educated guesses, estimates. An example might say a doctor may feel a patient has a 90% chance of a full recovery. That's just subjective probability, not based really on any mathematics. Sometimes it might be based on some empirical data from medical studies, but again, it's just kind of like a gut feeling. Last thing we should note is probability can never be negative. You can't have a negative probability. The smallest you could ever be is 0, and you need to be between 0 and 1. The largest you can be is 100% probability. So Got to be between 0 and 1. We're going to start by just identifying examples of each and then stating what the probability would be. So classify each statement as an example of classical, empirical, or subjective, and then state what the actual probability is. So let's say you draw a card out of a deck and it is a spade. So this is the type of probability here that we're using is classical, theoretical probability. And if you don't know, in a deck of cards, there are 4 suits. There are spades. There are something called clubs, which look like clovers. There are diamonds, and there are hearts. And these get used often, so it might be wise for you to, if you've never played with cards before, grab a deck and go through them. There are 13 of each. There are 13 spades, 2 through ace, or ace through king, depending on how you view it. There are 13 clubs. There are 13 diamonds and 13 hearts. So the probability you draw a spade would be 13 out of the 52 cards possible, which is 1 out of 4, or 25%. You can list it as a percentage or as a fraction. The results of a 1,100 people survey are shown. What is the probability the respondent is 15 to 24 years old? This is an example of using data. So this is empirical. I go over and look and I see there are 54 people between the ages of 15 to 24, and it was out of 1,100, so 54 divided by 1,100 I'll get as a decimal, and 54 divided by 1,100 is going to leave me at 0.05, which would be approximately 5%. It's about 0.049, but I rounded just to the nearest percent. So about 5% likelihood that they're going to be between 15 to 24 years old. So that's an example of empirical data, or empirical statistics. The two kind of tie together, and I mentioned this as an example based on the law of large numbers. So the law of large numbers states the following. As an experiment is repeated over and over, the empirical probability, that's what we actually see based on experiments, of an event gets closer and closer. It approaches the theoretical or actual probability of an event. So it might look like this. Let's say I toss a coin, 20 times. Maybe out of that 20 times, I only get 30% heads. Well, it's saying if I did that experiment more and more times with a larger number of samples, I'm going to get closer and closer to the actual. So instead of flipping the coin 30 times, maybe if I flip it 150 times, I will get closer and closer to that 50% heads and 50% tail situation. So it's saying if you do a large sample, you're going to get very, very close to the actual theoretical for your empirical probability. That's what the law of large numbers says. The last topic that we'll talk about is using what's known as the complement to find a probability. It's kind of like a shortcut. So let's go back to the survey question and consider another situation. What's the probability the respondent is younger than 65? And there are 2 ways that I could calculate how many people are going to be younger than 65. And the first option is just going to be add up the first 5 frequencies. All of these people are younger than 65, so I could just simply add all those values up. 54 plus 366 through 125. So 54 plus 366 plus 233 plus 280 plus 125 leaves me with 1,058, which means I'm going to get 1,058 divided by the 1,100 people, and that leaves me at about a 0.962. So 96.2% of that population that was sampled are going to be younger than 65. That's one way of doing it. Or instead, I could simply do the total number of people and subtract how many people are over 65, which is 42. So take the total, which is 1,100 people, subtract off the 42, and that is going to leave me with 1058. So there are 2 ways to find it. And in this case, it would have been much quicker to find how many people were older than 65 and then subtract that from the total. And we call that the complement, because the 2 pieces complete the entire population. So when it's smaller to calculate the opposite and then subtract it from the total, we can use this idea of the complement. So the complement is simply this. It's the set of all outcomes in a sample space that are not